Hi, Raja.
How are you doing?
I'm doing pretty well. Good timing.
Sorry?
I said perfect timing.
Oh, that's great. Okay. I will use my screen, right?
Right. I'm going to share. I'm going to make you the presenter now.
Okay.
And so that you will then share your screen. Yes. Okay.
So, Helio, do you see my PowerPoint?
Yep, I see it.
Okay, good.
Looks good.
Thanks. I will use the laser pointer. Do you see the pointer moving too?
Yeah, I see it. Everything looks good.
Okay, great.
Okay, we're all set.
Great. How many people do you expect?
I don't know. It varies each time. Sometimes as little as a dozen, sometimes as many as 60. This is the end of the academic year, as you know, for a lot of universities, and I don't think there are any big industry conferences going on right now. That sometimes conflicts with these, so we just have to kind of wait and see.
Okay, yeah. So it's our finals week, so things are crazy here.
Okay. Yep, I think finals are just about over here.
Oh, is it? Okay.
Yep. And for my benefit, can you tell me again what a SEPIC is?
It is a single-ended primary inductor converter.
Okay, got it.
Yeah, I think most people wouldn't know if I see that long acronym is what it goes by. So.
Okay. Roger, people are starting to log in now, but we'll wait a few minutes and start at exactly 12 o'clock.
Okay, sounds good, William.
Okay. Good afternoon, everyone. My name is Rogelio Sullivan. I'm with PowerAmerica, and I'd like to welcome you to this month's technical webinar. We have speaking today Dr. Raja Ayyanar of Arizona State University, and he's going to begin in just a minute. First, I'd like to say or ask you to please hold your questions to the very end after Dr. Ayyanar is done presenting. And then if you would use the chat function for WebEx, you'll find a chat option at the top of the toolbar for WebEx. Just type your question in there, and then I'll read the questions out so that everyone can hear them, and then Dr. Ayyanar will answer them verbally. It just works that way so that people aren't trying to talk over each other. So with that, I'll introduce Dr. Ayyanar. He is a professor at the Arizona State University. He received his PhD degree from the University of Minnesota in 2000. He's published over 150 technical papers on high-performance power conversion for various applications and holds 6 patents. He serves as an associate editor for the IEEE Transactions on Power Electronics. And with that, I'd like to introduce Dr. Raja Ayyanar.
Thanks, Rogelio, and thanks everyone for joining my talk. I'll be presenting our ongoing work under the PowerAmerica BP4. The title is Isolated Soft Switching SEPIC Converter. SEPIC, of course, stands for Single-Ended Primary Side Inductor Converter with active clamp, and the application is in a DC distribution rectifier, 480 volts to 400 volts DC in a data center. So this is a collaborative project between ASU and ON Semiconductor. The people working from the ASU side on this project are our postdoc, Deliang Wu, and 2 graduate students, Madhura and Tobin. And at ON, Jeff Pierce, Ajay Hari, and Anthony Nasser. They are helping us with this project. So outline, I will give a brief introduction about the project, what status we are in, specifications, and then delve into the proposed topology, basic analysis, design and simulation results, followed by our experimental details and experimental results. This is your 10 kilowatt, the final goal is a 10 kilowatt rectifier. So we use what is known as a phase modular approach. That is what the 3x2 means. So it's 3 phases, each giving 2 kilowatt for our Gen 1 hardware prototype. And then finally give some indication of where we are going next. Okay, project details. This is one of the BP4 started projects in the wide bandgap applications area. So as a BP4, the performance period is July 1st, 2018 to June 30th, 2019. We had a fairly late start. We started around end of September. So what I'm presenting is work done over roughly about 7 months time period. The overarching goal for this project is to develop and demonstrate a high performance and a fully modular rectifier for power conversion from a 3-phase 480 volts line-to-line AC source to a controllable nominal 400 volts DC bus. And the application area, as I mentioned, is in the data center. And of course, as being PowerAmerica sponsored project, we use a WBG device. In this case, because of the higher voltages, we use silicon carbide devices. So we have some really challenging targets. The efficiency for the complete PFC operation with galvanic isolation is 98% at the end of the project, and the power density also is equally impressive goal of 150 watts per cubic inch with isolation, EMI filters, everything considered. Okay, so an overview of where this project fits in. So this is your block diagram of a DC power distribution architecture that many data centers are moving towards. The input, as shown here, is from a 480 volts 3-phase AC. There is also a trend towards going directly from the medium voltage AC, like in the 12.47 kV levels. But our project targets a 480 volts input. And this is the scope of the project, going from 480 AC to 400 volts DC. And then this DC is distributed throughout the entire length of the data center, long distances. And then near the point of consumption, it gets converted to 12 volts, and then there are point of load converters on the processors and so on to convert it into 1 volt and below. So strictly for this power distribution architecture, galvanic isolation is not needed. But if you do have galvanic isolation, these are some of the major benefits that you can expect. It allows significantly better, easier management of faults, and also grounding becomes much easier if you have the galvanic isolation. And there is also the battery storage is already incorporated into the DC distribution. But if you also want to add, say, PV, which is also a DC output, with isolation, it becomes much easier to integrate these kind of distributed resources. And if you operate directly from the 13 kV, then isolation is no longer a choice, it is a requirement, because anytime you have such a high voltage conversion ratio from 13 kV to 400 volts DC, isolation is the best choice. Having said that, having outlined all the benefits, the isolation, the need for high frequency transformer is what makes the achieving the 98% and 150 watts per cubic inch power density extremely difficult, and that is something that we are addressing by a combination of topology, silicon carbide devices, and much improved magnetics. Okay, the specifications for what we signed up to do as BP4 project: input can vary from 380 to 480 volts line-to-line RMS. Output is controllable between 290 to 400 volts. We will develop a 10 kilowatt system, but the real applications is a much higher power level. And our approach is to use multiple modules of what we develop, these 10 kilowatt modules, several of them connected in parallel, will give us much higher power level. Power factor, greater than 0.99, THD less than 5%, EMI standard specifications, and the two metrics, efficiency 98% at the end of the project, and Gen 1, which is kind of what we completed so far. It's due end of Q3. So that has a 97% target, and power density overall project is 150, and for Gen 1 it is 1/2 of that. Switching frequency is 200 kilohertz, and that's what we use. Okay, here is the topology. So this is first of all a modular arrangement. Modular in two senses. First thing, it is phase modular. So even in just converter module that we developed, the 10 kilowatt module that we developed as part of BP4 project, even that is phase modular, meaning we have one converter for each phase A, phase B, and phase C. It's basically a single phase PFC with galvanic isolation, producing a regulated output voltage, and one for each phase, and they are all connected in parallel at the output after isolation. So it's modular in two different ways. We also interleave the three phases at the switching frequency level, so that especially the output current in this output capacitance, its ripple is significantly cancelled by the process of interleaving. That allows us to use very small capacitor. Note that this is a three-phase converter after all, even though we have three single phase connected together, it is a three-phase conversion. So there is really no 120 hertz ripple in the output capacitor. So that allows us to use a small capacitor. But if you negate that advantage by having to support a very large RMS current, then you would still need a high capacitance. So that's what this interleaving helps us. It reduces the RMS current through this output capacitor by ripple elimination. The topology itself within the single phase PFC is, after quite a bit of literature search and a very extensive simulation before the proposal, we identified the isolated SEPIC as a very good candidate, especially when you use this active clamp. So without this S2 and C2, this is a standard SEPIC. The S2 and C2 is the active clamp that gives ZVS for all the switches, and also makes the controller much simpler, as I will get to into in a later slide. The control arrangement is each of these phases have an individual input current controller. That's what shapes the inductor current to be exactly sinusoidal and in phase with their respective phase voltage. And there will be a single output voltage controller, and that can be high bandwidth as well, because there is no 120 hertz ripple to worry about. Then a few more features of the topology. When we go through the analysis, we'll see that both of the clamp and the main switch, it's a trade-off, but the most favorable trade-offs makes the switch stress something less than the 900 to 1000 volts range, around 950 volts. So that makes this a very good application to demonstrate the superior features of the 1.2 kV silicon carbide MOSFETs. The output also has a similar voltage stress, so again we use SEPIC 1.2 kV devices for the diode as well. All of the capacitors, there is a coupling capacitor standard for SEPIC, the clamp capacitor for the active clamp, and even the output filter capacitor. They are all low capacitance, fairly high RMS current, and they are implemented using film capacitors, all three of them. So what I'm showing here is the Gen 1 topology. So we have, in the process of doing this, we have come up with a new topology. It is a significant topological variation of what is shown here, and we will be applying for a patent. This has already been given as invention disclosure. You have all the PowerAmerica members have access to this. Okay, so very briefly, the operating principle. So this is phase modular, so if you understand fully well how a single phase operates, that's exactly how all the three phases operate as well. So what is shown here, this is really a rectified sine wave that comes after the diode bridge rectifier. And what I'm showing here, all these waveforms correspond to just one small, like one switching period, like 5 microsecond interval over a very large sine wave. So if you go to a different point, all of these waveforms will be slightly different. The concept is the same, but the magnitudes would be very different. So the first interval is when the main switch is on. So the corresponding equivalent circuit is here. The switch is on, so that's a short circuit. That will have the clamp switches open, so that is opened here. And so the inductor current flows through the switch. In addition, the transformer current, which now is primarily the magnetizing current. So some of the input and the magnetizing current also flows through the switch, and the coupling capacitor supports the magnetizing current. So that is all of this region here. So even before that, let me also mention the capacitor voltages. The coupling capacitor, you can do a very simple analysis to see that it follows exactly the input voltage, which at this instant of very zoomed in. So this is the capacitor voltage, 400 volts. That is what I zoomed near the peak of your sine wave, 400 volts. The clamp capacitor charges to the reflected output voltage plus your higher voltage, depending on what the turns ratio is and the value of the leakage inductance. So for the given specification, that is around 600 volts. So during this interval, the transformer current is mostly the magnetizing current, because when you have the switch on, this coupling capacitor voltage, which you saw was 400 volts, that is applied as a negative voltage across the primary. Therefore, the secondary is also negative. That reverse biases the secondary diodes. There is no secondary current or primary load current, only the magnetizing current. The next interval is when I turn off the main switch. So immediately this current, input inductor current, is same as phase line current, that now flows through the coupling capacitor through this diode of the clamp switch into the clamp capacitor. In addition, the magnetizing current also flows through the clamp capacitor. Now that we are applying the clamp voltage across the primary and the leakage combined, now it is a positive voltage that will forward bias this diode. So in addition to the magnetizing current, you also have the reflected load current component. And the voltage across the leakage inductance is shown here. So that will be the difference between the output voltage reflected to the primary side and the clamp voltage. So about 600 minus 400 that is applied across the leakage. That makes the load current, the leakage current increase, as shown here. That makes the clamp switch current fall down. And initially it is all negative current, meaning it flows through the diode, and then eventually the current direction will reverse and flow through the MOSFET. The third interval starts when you turn off the clamp switch, and then you kind of enter this one till the load current has a chance to die down to zero. This also happens, limited by the leakage inductor providing d over dt limitation. So the main thing to see is that this region, when the coupling capacitor current is higher than the input current, that is what critical to achieve zero voltage switching for the main switch. And for the clamp switch, you have really long duration. Till this point, as long as this current is positive, the diode will be conducting, and you can choose to turn on your MOSFET any time during this region to achieve ZVS. Another unique thing about having this active clamp and fairly large leakage inductance is that this is the diode current. You can see that it has a very low dI over dt. So even if we use a standard silicon diode, there will not be a significant issue with reverse recovery. Of course, we use silicon carbide, so it's not a major issue anyway here. But the issue is we do have junction capacitance that causes ringing and related losses, which I will get to in a different slide. So this is analysis over just one switching period, but of course this is operating over, the input is really a rectified 60 hertz sine wave. So these waveforms show what happens over your complete fundamental period over 16.66 milliseconds duration. So most of these waveforms have this sinusoidal envelope. This is the input inductor current. This is shaped to be sinusoidal and follow the input voltage. The primary current has a sine envelope, so do most of the capacitive currents and coupling capacitive currents, even the diode current. So this is again zoomed on near the peak to show that the peak voltage stress of the switch is around 925 volts, and the peak voltage of the diode is around 774 volts. It also shows the capacitor voltage stresses, so we need to use a 600 volt swing capacitor, and as I mentioned, 1200 volt silicon carbide devices. So some simulation waveforms to show the advantages. Of course, these are the three-phase currents, so we can get in a perfectly sinusoidal or very close to unity power factor, so it's very easy to achieve. And then this is the output voltage. This is just with a 20 microfarad filter capacitor, even for a 10 kilowatt application. You can see that the absence of low frequency component in the output voltage, even with 20 microfarad. And this is the significance of interleaving. So these are the three diode currents from the three-phase converter, and this will be the total current that goes into the capacitor and the load combination. So if you did not have the interleaving, then you will not have this more like not exactly continuous current, but you have current almost throughout the entire region. If you did not interleave, there will be only one current during a small interval, no current at all for a long interval. That results in extremely high peak current and high RMS current. So we might end up losing the benefit of no 120 Hz ripple and still use high capacitance. That issue is solved by this process of interleaving. Okay, so another set of simulation waveforms to show the zero voltage being achieved. So the left wave, this waveform corresponds to the main switch. So this is when the gate voltage is applied, and you can see that well before that is applied, the diode source voltage has come down to 0, and the current is actually negative, meaning it flows through the diode. This is the clamp switch. Here you have much more leeway to achieve ZVS. The current is still negative much after the device is turned on. So we get zero voltage turn on. Turn off would be not completely zero voltage, but low voltage, and we even put some extra drain to source capacitance across our silicon carbide MOSFET in order to limit the voltage rise when the current is falling. To illustrate the advantage of zero voltage turn on even for wide bandgap devices, this is from our the three devices that we're using. These are the turn on and turn off energy switching loss during the turn on and turn off process. You can see that the turn on energy is still about 4 to 5 times larger than the turn off energy. So if we can make the turn on switching energy loss 0 by the process of ZVS, you are guaranteed to get very high efficiency even at frequencies in the range of 200 kilohertz and above. Okay, so from simulation we did a very detailed loss breakdown. So our goal, as I mentioned in the earlier slide, was 98%. So simulation, so this number corresponds to about 98.1% efficiency. The major losses happen in the rectifier bridge because this is fairly high current and the diodes have close to 1 volt drops. That's one major component, rectifier bridge, about 18 watts or 29%. The other, probably the biggest loss component is in the transformer itself. 30% of the losses go in the high frequency transformer. Then about 10 watts or 16% loss in the output diode and other some smaller losses. So we will be addressing the magnetic losses and remove the diode bridge rectifier, and that is what our Gen 2 topology does for us. Okay, moving on to hardware. So this is our circuit layout. So the transformer, both transformer and the eventual input inductor, they will be using planar ferrite cores. These are the 3 capacitors, coupling, clamp, and the output capacitors, 2 MOSFETs and the output diode, the bridge rectifier, EMI filter, and the heatsink that goes on top of all of the 4 devices. So it's also a good place to talk about the power density. The size is shown 4 inches by 6.5 inches, and the height for each phase is 1 inch. So that results in 26 cubic inch for one phase. And for Gen 1, our power level is 2 kilowatt. That gives us a power density of 77 watts per cubic inch, which is slightly better than our target of 75 watts per cubic inch. Gate drive, as in any high frequency, especially using WBG devices, is a very critical part for reliable operation, as well as to get the benefit, low switching loss benefit of wide bandgap devices. So we take a lot of precaution, a lot of care to make this as perfect as possible. And as a result, if you look at, these are switching waveforms at almost the rated power. I think it's 1.5 kilowatt, where the rated power was 2 kilowatt. You can see very little ringing in the VGS waveform, and the VDS waveform is also a good place to see that we do achieve full zero voltage switching. This is a gate voltage, and the VDS one, the blue waveform, it reaches zero well before the gate voltage even goes above zero voltage. So it's a zero voltage switching. There is this ringing, which I'll talk about. This is because of the resonance between the output diode capacitance and the leakage inductance that we need. We need actually a high value of leakage inductance to achieve zero voltage switching. So magnetics is the biggest challenge. There are in any converter, magnetics, high frequency magnetics is it's a challenge to achieve power density and efficiency. The extra 1 to 1.5% loss in the transformer would typically compromise the overall converter efficiency. SEPIC has even more challenges. That is because if you look at, so these are the transformer waveforms. This is the primary voltage waveform. If you zoom in, it will be switching between the output voltage and the coupling capacitor voltage, which has the sinusoidal envelope. More importantly, this will be the flex waveform in the core, and it has this very large 120 hertz component. So we need to take care of the peak flex, just like in our input inductor, which has this 60 hertz component. Here also we have the 60 hertz plus the 120 hertz component. So it is not only limiting the high frequency ripple, we are also designing such that even at the maximum flex density, the core does not saturate. And the SEPIC also has fairly high pulsating currents, and especially for a PFC application. So the RMS current for a 2 kilowatt is as high as 15 amperes RMS. So those are some challenges. We are trying to address them by fairly detailed finite element analysis, planar EE cores. We are trying many different core materials and many different core geometries, and many different combinations of winding arrangements, including lathes, which is what is shown in all of these 4 iterations. We are also looking at copper foil and, of course, PCB-based windings. So these are some of the different winding configurations that we tried. This is fully interleaved. This is all primary and then all secondary on top of them. Here, primary on the top layer and the secondary on the bottom layer. And so far, at least, what has worked best for us, what gave us highest efficiency, was this arrangement 3, because in this active clamp SEPIC, we need fairly large value, is like 10 microhenry, and this arrangement is what gives us that leakage. With the interleaving, even though the transformer itself may be slightly more efficient, we are forced to have a separate leakage inductance, external inductor, and the size and the losses in that is not a good trade-off compared to 3. Okay, modeling and control. Another very big benefit of active clamp is it makes the plant transfer function, basically the D to the input inductor current, D to IL plant transfer function, much easier to compensate than a standard SEPIC converter. So if you work with SEPIC, you will know that it is fairly a complex converter to control. It is really a 4th order transfer function because it has this coupling capacitor, the LM, output capacitor, and the input inductor that makes it a 4th order system. And so this part is what you would get as the D to IL transfer function for a standard SEPIC. So mostly people use a snubber circuit across the coupling capacitor, fairly large lossy RC snubber across the coupling capacitor that will give you these transfer functions shown by this dotted line. But with active clamp version, we don't need that snubber. Even without that, it gives probably even better performance than the snubber-based SEPIC. So these are some comparison of the plex simulated frequency response and the measured response from a network analyzer. And they show fairly good results, but more importantly, it is a much benign transfer function to compensate. The gain does depend on the input voltage, but not too significant. So we could potentially think of using variable gain control, but our experience has shown that simple PI controller gives very good results for the current loop, and that's what we're using currently. Okay, some power quality results. So we are very excited to get really very good current waveforms. So these are at the 2 kilowatt, our Gen 2 goal of 2 kilowatt. So at the almost the rated input voltage, close to 2 kilowatt power level. So this is the inductor current waveform, and the smaller one is the input voltage, phase A, and the one right on top of that is the input current. The THG is as low as 2%, whereas our target is just less than 5%. So we are well above meeting that target. And the power factor, of course, it's for all practical purposes, it's just 1 unity power factor. And that is confirmed by all of these power analyzer waveforms. More hardware results. This corresponds to zero voltage switching. So we get full zero voltage switching, meaning the drain to source voltage comes exactly to zero before turning on the gate for much of the operating region along the sine wave. And only near the zero crossing of the sine wave, we lose ZVS. We operate under partial ZVS or partial hard switching. And that is again a trade-off. We could design the leakage to be extremely high and try to get ZVS over almost a full range, but that will not result in the best, the maximum system efficiency. So it's a trade-off, and for our trade-off, we do have some hard switching near the zero crossing. So this waveform is zoomed in near the peak. So again, you can see the VDS, this waveform here, is around 700 volts level, comes to zero by itself before the gate is turned on. Same thing here, and for near the zero cross, you can see it comes down resonantly up to this point, and after that, this is when the switch is turned on, and then goes to zero almost instantaneously after that. Another benefit of zero voltage switching, the gate voltage is not shown here, but the zero voltage switching significantly improves in the quality of the gate voltage as well. Okay, so I've been alluding to this problem in a few slides earlier as well. So this is the ringing caused by the resonance between the capacitance of the output diode, which is fairly large, with the through the transformer, the resonance with the leakage inductance. So initially, this diode was conducting. There is interval 2 that I showed in the earlier slide. Then when I turn on the S1, the current reduces, and eventually the diode current reaches 0, and the diode should turn off. Once that happens, this capacitor begins to charge. You should just charge to the output voltage plus the reflected secondary side voltage, but then the resulting just goes beyond that. There is no damping. It goes actually twice the expected values. The expected value is around close to 700 volts, so it could theoretically reach as high as 1,400 volts. In actual hardware waveforms, we do see it go up to 1.3 kV. So there is a problem for 2 reasons. One is the very high voltage stress. We are actually using 1.2 kV devices, and actually the device survived even 1.3 kV application for fairly long duration. But obviously, we don't want to operate that way. It's not reliable. So that's one main reason. The second one is the losses associated with that. So it's mainly the damping is done by the extra high frequency current through the core. So this core losses modeled by this resistance, that is where much of the damping happens. So losses about almost 1% is what we observed because of this resonance phenomenon. So we came up with several clamp techniques. A, B, and C. A is suitable if it's a non-isolated version. B and C are suitable if it is an isolated version, as in our case. All we do is we add another additional winding. This does not process any power. It is just a very small single strand with same number of turns as the secondary. and that is either connected, as in this case, to the output load, or in case C, to the input source. In either case, instead of dissipating this energy stored in the output diode capacitor into core loss or into the series resistances, it actually releases it either to the output load or to the input to be used later. So the benefit is, if you look at B and C, which is B is what we're implementing, instead of 1300 volts voltage test, it is now reduced to less than 900 volts, so we can reliably use the 1.2 kV devices. More importantly, the losses also are reduced by 12 watts, which at 1 kilowatt testing. So that's roughly 1% efficiency improvement, which is a big deal, given our target is 98% efficiency. Okay, so coming to efficiency, so we have almost met our Q3 Gen 1 goal, which was 97%. The efficiency we achieved at 1.5 kilowatt was 96.45%. This is for the full PFC mode with galvanic isolation. I say full PFC because we also do testing as a DC-DC converter, which has slightly more efficiency than a PFC mode of operation. So this is the full expected operation, and we are close to our target of Gen 1, 97%. Okay, Gen 2 topology. So this is what we filed an invention disclosure, and we will soon be filing a provisional patent. So I have not shown the circuit, but PowerAmerica members have the access to at least the invention disclosure, as shown here. So what is new here is it is still a SEPIC-based topology, but it is you can think of this as more of like a totem pole version of SEPIC. So it still has 2 high-frequency switches, but it has, instead of 4 diode bridge rectifiers, it has just 2 diodes, or 2 high-frequency diodes, or 2 low-frequency switches. So that reduces significantly the conduction losses. Instead of having 3 devices in series at any given instant, you only have 2 devices, and even the diode with this synchronous rectifier with the MOSFET across that at low frequency, that also reduces the drop across that device. Instead of 1 volt, we can make it significantly lower, and that, together with the fact that only 2 devices are operating, reduces the conduction losses significantly. There are also other advantages. We can use the DC link capacitor to provide some limited support for 120 hertz power pulsation, which is significant for single-phase applications. Operation-wise, it is more or less similar to what I described, just that we don't have a separate main switch and active clamp switch. The functions are done by combination of the 2 high-frequency switches. So during positive off cycle, one acts as like a main switch, and other as the active clamp, and vice versa for the negative off cycle of the sine wave. Okay, so this topology is what we're using for our Gen 2. We have just started work on that. We have actually built the prototype, and these are some preliminary results. The very first result of assembling it and just doing the very first test. Nothing is optimized yet. Even then, we are able to get full 0 voltage switching as confirmed by VDS2 and VGS2. VGS2 well before it rises beyond 0. VDS2 is 0, and the gate voltage looks fairly clean. For this generation, we're using ON Semiconductor's gate driver NCP51705. The efficiency, at least under the DC-DC test that we're doing with isolation, is 98%. Okay, so to conclude, so we have a high efficiency, high power density solution, primarily targeting data center application, and this the topology is it exploits the benefits of the 1.2 kV silicon carbide devices. But I just want to emphasize that both the basic topology, Gen 1 topology, and more so the Gen 2 topology, they are very well suited not just for the data center applications, but for a much wider spectrum of applications. In fact, anytime you need AC-DC PFC with galvanic isolation, this is something that you could seriously consider. Some other applications is primarily in onboard charges for electric and hybrid electric vehicles, telecom data center rectifier, which is what kind of we are doing for PowerAmerica, and at much lower power level as a single phase PFC. It is also very well suited for LED power supplies. Okay, that was my last slide, and thanks for attention.
Thank you very much, Roger. That was an outstanding presentation, very comprehensive and thorough description of your development. Can you tell me what is ON Semiconductor's role in the project?
Very significant. So, Anthony Nasser, who is both an ON employee as well as he's doing an MS with ASU, his role is in the complete EMI filter design. So that is his main contribution. And they're also helping out significantly with the layout and as I mentioned, the gate driver is from ON Semiconductor. So they provide us support not only with parts but also in the design, especially as you know, gate drive is a critical component of any wide bandgap based converter, especially at high frequency. Mm-hmm. So they completely take care of that, and they also give us advice on the magnetics. Even though the finite element analysis is done by us, some of the like which core gives us the lowest losses under what frequency range, those kind of information from their experience. Those are going to be extremely useful.
Okay, great. Sounds like a good collaboration. Okay, the floor is open for questions. If you have any questions for Dr. Ayyanar, please type them into the chat window, and I'll read them out. We have time, so please take advantage of this opportunity.
Hey Raja, this is Swanand here from Eaton. I have a question on how would you scale this design to say, you know, if you wanted to do 100 kilowatt three-phase power, how would you scale it? Would you put, you know, multiple of these in parallel, or would you, you know, just use high current devices?
Yeah, so we would still use a modular approach, but then not paralleling, like if you want, you know, 500 kilowatt, we'll not be putting 10 kilowatt as many as needed, 50 of them as needed. Probably we'll build your 50 kilowatt prototype using higher current devices, and then use 10 of them to go to 500 kilowatt. That would be a more practical approach. The converter itself is designed for handling extremely high modularity. Yeah.
Oh, so you think this is easier to parallel up to 10 modules?
I would, yes, yes.
Okay. Okay, thanks.
Are there any more questions? Okay, Roger, would you please send me a version of the presentation that you're willing to share so that I can distribute them to anyone that joined the webinar today?
Yes, certainly I can do that. It will be public, right?
Yes.
Yes, okay.
It has to be something you're willing to share publicly.
Yes, okay. Yeah, I will send that today.
Okay, that was the one question that came through. If there are no other questions, going once, going twice? Okay, thank you very much. Thank you all for joining us today. And again, thanks especially to Dr. Ayyanar. Really appreciate your time and obvious preparation for this. Really enjoyed the presentation.
Great, my pleasure, and thanks everyone. Bye now.
Bye.
Thanks, bye.